take a look at what's happening energetically in that addition reaction. Remember, we have bonds broken and we have bonds made. So the bond's broken. We have a carbon-carbon pi bond that breaks, and of course we can measure that energy of that pi bond is 66 kilocalories per mole. We also have a hydrogen-chlorine bond that's breaking, a sigma bond that's breaking, that is 103 kilocalories per mole. So a very strong bond that requires energy to break that bond. So notice these are going to be bonds in which we have to add energy to break them. Then we have bonds that are made. So we have a carbon-hydrogen sigma bond, and so it's going to release 96 kilocalories per mole of energy. We also have a carbon-chlorine bond, which is a little bit less energy, but still 85 kilocalories per mole of energy that is released. So we have to look at kind of the net effect is that I have to add the 66 plus the 103 kilocalories per mole of energy to break those bonds. And then in the process, I release the 96 and the 85. And so the total is a release of energy of minus 12 kilocalories of energy per mole of reaction. So overall, this is an exothermic reaction, we say. Now, keep in mind, the reaction isn't that simple because it actually takes two steps for the reaction to take place. The first step is the formation of the carbocation, right? The breaking of the bonds. The second step is the making of the bonds. So this isn't happening in concert. It's happening in two different distinct steps. And when we think about the energy diagram, then we can think about it in the two distinct steps. So the first step involves the formation of a carbocation. Now, carbocations, remember the carbon has only 6 electrons around it. It doesn't have an octet of electrons, and therefore it's going to be an unstable intermediate. It's going to require energy that we have to input to form that carbocation. And if we think about an energy diagram where we have, plotting energy on the y-axis and our reaction coordinate on the x-axis, and we kind of envision at the molecular level what's taking place in the reaction. And we start at some arbitrary energy level where we have the alkene and HCl. And so what's happening? Well, they start to come together and they start to form a reaction that's taking place, right? The pi electrons are starting to donate to the hydrogen, and the HCl bond is starting to break. Well, we're going to have to overcome electron-electron repulsions and overcome the stability of the instability of that carbocation, and therefore we have to add energy to form that carbocation and to form the chloride ion, right? Now, that energy required, that maximum peak there is what is referred to as the transition state. So we have this transition state to form the carbocation. And we can envision what that transition state looks like, where we have now that carbon pi bond is starting to break. Electrons from that pi bond are starting to go to the hydrogen, and the hydrogen-chlorine bond is starting to break. So I'm denoting those all as dashes because they are in transition. The electrons there are moving around, right? The electrons from the pi bond are actually disappearing to form a new carbon-hydrogen bond, which is starting to up here, and the hydrogen-chlorine bond is starting to break. And in that process, notice the carbon starting to take on a partial positive charge. The carbon on the left is because it isn't accepting, it's actually donating electrons. It happens that the center carbon is going from one bond to another, and therefore it's neutral. The hydrogen's going from one bond to another, so it's neutral as well. But the chlorine is going from a neutral charge now to a negative charge, so it's starting to take on a negative charge. We say it has a partial negative charge associated with it. This is what we refer to as the transition state. And we find this based on what's called Hammond's postulate, which says that the transition state is going to be similar in energy to the basically to the highest or the closest energy either reactant, product, or intermediate. So it starts, in this particular case, it's going to resemble that of the carbocation, but that's how we represent that transition state. Now that's the first step. The second step, what's happening there? Well, it happens rapidly because the carbocation is very reactive. It is a strong electrophile, so it's seeking electrons. And where is it seeking? Where is it going to get the electrons? Well, again, we can plot an energy diagram where energy is, again, the y-axis against our reaction coordinate. And now here we're starting with the carbocation and the chloride ion, and a rapid reaction occurs. And it's an exothermic reaction, as we saw, because we're now forming bonds, and so energy is released in that process, and it produces now our product, which is an alkyl halide. And now that alkyl halide is much more stable than our intermediate carbocation. Again, we can think about the transition state of that process in which the carbocation carbon is now accepting electrons from the chlorine. So now as chloride comes and donates its electrons, it's losing some of its negative charge, and so it doesn't have a full negative charge, it has a partial negative charge. And the carbocation is losing its positive charge. It becomes neutral, and therefore it's now only a partial positive charge. That's how we demonstrate the transition state of this second step. And so now we can put it all together, right? Putting both of them together, we see that the alkene is going to react with HCl. I need a lot of energy to overcome that hurdle, right? That's going to be our slow step, our rate determining step in the process, because I have to add energy to get to the carbocation. Once the carbocation is formed, then it rapidly reacts to form our product, alkyl halide. And in the process, we have two transition states. The first transition state, which I demonstrated below. I'm not going to show it here again for simplicity's sake. And then the second transition state, right, where the chloride is coming in and reacting with the carbocation. And now I have a picture of the whole reaction in its entirety and what the energetics of that looks like.